Quantum computers are supercomputers equipped with advanced processing powers.
Hi, I'm Greg McClendon. I'm studying externally. Today I'm presenting a discussion on quantum computing.
Nothing like a mini montage to prepare you for what's to come. Be warned, this presentation may hurt your brain. Today we're going to cover an overview of quantum computing technology, its uses in industry, and where the technology sits on the Gartner hype cycle. So what is quantum computing? A quantum computer can process massive and complex datasets more efficiently than classical computers. They use the fundamentals of quantum mechanics to speed up the process of solving complex computation. Often those computations incorporate a seemingly unlimited number of variables. Here we can see venture capital companies, D-Wave and IBM's version of their quantum computers in use today. So what makes a quantum computer faster than a classical computer? Classical bits, stored on transistors, are the basic units of information processing in a classical computer. They are basically electrical on-off switches embedded in microchips that alternate between 0 or 1 to process information. It's sort of like a light switch which can only exist as off or on. The more transistors on a chip, the faster the chip can process electrical signals, and the better a computer becomes. But as modern technology evolves, it will generate richer data sets that require additional computing power. Quantum computing is what comes next to meet the needs of modern technology. Quantum computers do not use classical bits. Instead, they use qubits. Qubits are the basic units for processing information in a quantum computer. Qubits can be any value from 0 to 1 or have properties of both of these values simultaneously. In other words, unlike classical computing architecture, quantum computing processing occurs simultaneously in multiple states. Right away, there are a whole lot more possibilities for performing computations, which in turn mean they can store a massive amount of information while using less energy. There are three types of quantum computers based on the number of qubits they have. To date, there has been limited use of quantum computers using quantum annealing computers. These computers focus on solving specific optimization problems, such as optimizing the design of an aircraft wing in all directions and wind speeds, or calculating the most cost-efficient travel and logistics for cars in overcrowded cities. Processes that would take years for a classical computer can be done in hours for a quantum computer. Quantum simulation computers will need more processing power, but they will be able to run simulations such as protein folding to develop cures for diseases. And finally, universal quantum computers, which are theorized to have more than 1 million qubits, will be able to tackle any massively complex computation and get a quick solution. I did warn you that I was going to hurt your brain, right? Don't worry. The main takeaway is that quantum computing is more powerful and capable of processing far more data and complex calculations than existing commercial computers. Quantum computing has been under development since just before the turn of the century. So why is it taking so long for us to get quantum computing readily available on a commercial scale? Well, traditional laws of physics don't apply at the quantum level. Quantum computers rely on quantum mechanical states of matter known as superposition and entanglement. The unpredictability of qubits means that computer engineers are still performing lots of simulations and experiments to determine how to write software for quantum computers. It's expected by 2030, quantum computers will outclass the best computers we have today. Quantum computing will have implications across different sectors. Healthcare, comparing the interactions and effects of different drugs on a range of diseases to determine the best medications or more efficient genome sequencing that is done at a global scale. Portfolio risk optimization and fraud detection and stock market prediction for financial services. Cybersecurity, to break cryptographic codes that we use today and keep sensitive data communication secure. However, quantum computers could also be used to secure data from quantum hacking. Agriculture quantum computers could help us more efficiently make fertilizers, or quantum cloud computing could simplify programming and provide low-cost access to quantum machines. In the distant future, quantum computers could be used to calculate the field of artificial intelligence. Training AI on quantum computers could advance computer vision, pattern recognition, voice recognition, machine translation, and more. The Gartner Hype Cycle for Emerging Technologies in 2005 positioned quantum computing on the technology trigger slope and predicted a plateau of productivity would be reached in more than 10 years. Interestingly, the 2018 Gartner Hype Cycle, 13 years later, still had quantum computing at the innovation trigger slope, which, with a predicted plateau of productivity now narrowed down to 5 to 10 years. This pattern is reflected in the number of investments made in the quantum computing R&D space. Given the growing interest and an appetite for funding in this field, I get the sense that quantum computing will be commonplace in the coming years, despite what some users may think.